Howdy, hey, hi, Spaceman Josh here. And so I wanted to take a step back because I know that my last vlog I talked about the geometry of space-time, and I think I may have jumped the gun a little bit, and I want to take a step back and sort of explain what really is space-time. And so I think starting off, something that I'd sort of begin with, think about three-dimensional space. Take a look around you, look at the things around you, whether it be yourself or just different objects in the room that you're in, and take a look at different things around you and think about how, the size of them, the shape of them, how they are in space at this moment. You can even, take a look at your hand and sort of move your hand around a little bit and just think about the different ways that your hand is in 3D space and how it's sort of moving along it. And sort of, it gets pretty interesting to try to think about, but it's something that it's something to begin off. You want to talk about the sort of 3D space and try to just visualize in your head about what it sort of the shapes and the way that the object itself exists in three-dimensional space. And on top of that, everything everything that you can see also is moving through time. Time is not something that never really sits still, and so everything that, even if it's not moving, it's moving through time, even if it's not moving in the 3D space. And so a lot of things that can have sort of contributions to the understanding of when we want to try to do, say, if we wanted to try to do space travel at speeds close to the speed of light, having an understanding of space-time and different things in general allows us to have a better understanding of what's going to happen. And so we have what's called a space-time diagram, where you look at how an object moves through space and time at the same time. And so I know that in the last video I showed you sort of a graph of something along that sort of used two space variables and then the time variable. This time I have up here on my whiteboard, I have something for only just one space variable and then time. And so on sort of the horizontal axis we have x, which is just a way of describing one spatial time variable. There's the common conventions are x, y, and z for space, and we're just using x to denote just one variable and for three-dimensional space. And then we have ct. C is the commonly used letter for the speed of light, which is so a lot of people say it's 3.0 times 10 to the 8th, and that's something that's using scientific notation. The entire number up to the ones place, if my memory serves me correctly, is 299,792,458 meters per second. And so that's basically what C represents, and then T is just time. And the reason we have CT is because C is in units of meters per second, and then time, when you talk about in terms of units as in seconds, using this method called dimensional analysis, you essentially are just left with, when you multiply those two together, a unit of meters. And so we can talk about x as in units of meters because it's in space, 3D space. You can measure length in meters. So we can have meters on one axis, meters on another, and it allows us for an interesting sort of way to look at a graph. And so with a lot of these things, so we can start to think about how we what an object looks like when it's traveling. And so first thing we can look at is, what is it like? What does light look like on this graph? When light travels at the speed of light, what does that look like? And for this graph, it's actually it's going to sort of look a little something like this, where you essentially, if you start from the origin, which the origin is when the two lines meet, if you don't know that, at the origin it would follow a 45-degree angle between CT and X to sort of go off in that way, and because the amount of distance it travels in meters would be the exact same as the amount of distance that it traveled along CT, because this CT, if c is the speed of light, that means that the distance when you travel by the time that's passed is going to be the distance traveled along the certain x. If that makes any sense, it can be kind of complicated to think about, but essentially, at any point along this line, CT and X along for these points are exactly the same. And so it creates an interesting sort of dynamic, and I'm going to draw another 45-degree angle line sort of here, sort of denotes, sort of, if you saw the last video, denoting sort of the light cone. And I'll get to that in a minute, but I also want to talk about what an object looks like when it's traveling slower than the speed of light. And so we try to think about this. So in terms of so with CT, let's say that so CT, let's say goes the same amount, and so let's say we get so we start at the origin, we have an object traveling slower than the speed of light, and we want to go, say 10 seconds in the future, and so CT is a certain value, and if something is traveling slower than the speed of light, and if you say, let's say 10 seconds was this thing that I marked right here, let's say the 10 seconds times the speed of light is that marker right there, then an object that's traveling slower than the speed of light in terms of the x wouldn't reach this point. It would reach some sort of point beforehand. And so we can sort of think about sort of that line that you can draw for an object traveling slower than the speed of light. And one thing you can immediately notice is that it is inside the light cone, which is good. That's something that we want. And so we have this line, and it's actually steeper than the line for light traveling on space-time. And you can take that all the way to the point where you think about what happens when an object is not moving at all. And so, let's say it just starts at some length x, and it's just some x length away from the origin of our axes, and it's not moving at all. So in terms of x doesn't change because it's not moving. However, it's still traveling through time, and so we sort of denote that in a way of it goes sort of along just a straight line parallel to the CT axis. So this would represent an object that's not moving in terms of 3D space. It's not moving, however, it's still traveling through time. And so that's sort of, this is sort of generally how we put objects that are moving along a space-time diagram. And if you have something that starts off and it's not really moving that fast, but it starts to accelerate towards the speed of light, you sort of say it goes into a negative x direction, which means it'll be going sort of that way along the axis, starting at the origin. You'd have something that starts really, really steep, but then curves to sort of go off and sort of that way. And it'll get closer and closer to 45 degrees, but a little bit interesting thing here is it actually never will actually hit 45 degrees. But it'll go towards 45 degrees, and so it sort of starts near parallel when it's moving, and it tries to go towards 45 degrees, and that's something that you would be accelerating towards the speed of light. And so we sort of, that's generally an idea of how we want to graph things that are traveling in space-time. And it gets even more complicated when you add more variables into the mix. And you can try to conceptualize if you want. You can try to find other videos that try to go into that. I'm not going to go into that here because, like I said, that gets really complicated really fast. And so now I do want to take a minute and talk about the light cone that I had. So I'll go ahead and take my blue marker and redraw sort of that light cone that I have here. So we have this light cone, and we actually have different areas for the light cone. Say we had an object that was at the origin, and so when you want to talk about anywhere an object could have come from, anywhere where an object could have been and then traveled to the origin, you have to talk about anything anything inside this light cone, sort of below, anything down here. And this is essentially talking about the past for this object. This object had to have come from somewhere inside this area of the light cone in order for it to be at the origin. And then so sort of in sort of in the opposite direction, anywhere above the light cone is an area where it can travel. So anything sort of up here, in a way, is anything up here, we sort of talk about as the future potential areas where the object could travel to. Essentially, it can't travel anywhere but inside sort of this area of the light cone. And then sort of we have these areas sort of out here that are outside the light cone. Now, if you are an object at the origin, going anywhere in this area would require you traveling faster than the speed of light. And because of different various things involving general relativity and different laws of physics, you can't travel faster than the speed of light. But this area still has a name. It's called the Elsewhere, which I think is really sci-fi-ish, and it's really cool. So we call both sides of it the Elsewhere. And now that we sort of understand that, and this is sort of a mess, I'm going to go ahead and put it down. So then now we can start talking about sort of looking in 4 dimensions. So it's essentially the same like looking in 3 dimensions, except trying to conceptualize the idea that everything you see is in the past. So when you're looking at an object, the way you see that object is sort of a light comes from whatever light source it comes from. The light bounces off an object, and then has to go and reflect off in a direction and it hits your eyes, and that's how you see the object, is the light reflecting off that and then going to your eyes. For a very simplistic version of optics. So with that, it takes time for that light to have hit from the time that light hit that object to getting your eyes. It took time for that to happen. Now your brain is actually very good at sort of fixing that, in a sense that say you look at an event, and at the same time just a few milliseconds later that event makes a sound, and it's just barely off sync from the actual event happening. Your brain will actually adjust that so you think and you actually hear and see those 2 things happening at the same time, because your brain is thinking that it's the same event, therefore it needs to happen at the same time. Your brain is good at making you sort of see things in that way. And similar thing with with light, with the amount of time it takes from the light to travel from my hand to my eyes, the amount of time in that is so small that my brain it's not looking at it as it's in the past. It's looking as if right now that's what my hand looks like, and it has the different senses along your body to be able to interpret it that way. And so it doesn't feel like you're looking at things in the past, but because of the time that passes is so small, it's basically negligible. It's basically 0. For example, I've done the math for if something was, say, 106.9 kilometers away, and so for those who use the imperial system, that's technically 99.98 miles, but you can just round that to 100. So if something's 100 miles away, or 106 point not, sorry, math wronged. If it's 160.9, that's the correct term. 160.9 kilometers, which is about the same as 100 miles. If you had an object that far away, and the light bounced off that object and went to go to look into your eyes, the amount of time that would pass while the light was traveling from that object to your eyes is about 0.5367 milliseconds. Or, if you're more familiar with some other prescripts, it's the same thing as 536.7 microseconds. And so what that basically means is about 0.5 milliseconds of time passed from that object from light hitting that object, and then the light bouncing back to hit your eyes so you can see that object. It took 0.5 milliseconds for that light to travel, and so it's basically negligible to your brain. So you see that object as if it was in real time. That's how you interpret it. However, you were technically looking at that object how it was 0.536 milliseconds ago. So everything you see, you're looking at something in the past. It's that sort of idea of you're looking in 4 dimensions. You're seeing everything in 3D space as it used to be at some time period ago. And the farther away you're looking, the older that object is. And that actually has a lot of implications with astronomy and looking at objects that are billions, millions, essentially in between, the difference between 2 million light years away, or 20, or sorry, that can't, 10 billion light years away. That's a distance we can look at. Essentially, that difference, where if something is 2 million light years away, it took light 2 million years to reach us. So we are looking at that object as it was 2 million years ago. This is really where thinking about that, looking in 4 dimensions, actually comes in handy. Where something's 10 billion light years away, we're looking at that object in 3D space, but we're looking as it used to be 10 billion years ago. And so that's really the idea of space time, and how an object exists within space time, and how we have to. If you think about looking in 4 dimensions, you're looking at the object in 3D space as it was in some time frame that before the light got to your object. It's a very interesting concept, and I highly recommend you try to look at different videos that explain it way better than I do. But that's all I really have. So if you like this, go ahead. If you like the video, go ahead and hit subscribe. So that way, if you want to, you can hit the bell and turn on notifications. Get told when I upload. I do these vlogs, these educational vlogs, weekly on Sundays. And so that's thank you for traveling with me. Spaceman Josh, out.